Sarah. Thank you for having me. First question, everybody's able to see my screen, right? Perfect. All right. So it's interesting. You say I'm from Kutztown University. I think we're from two vastly different areas because on the way in, I had to pass up a Amish horse and buggy. I live right outside of Amish country. So two very different things going on right now between Kutztown and Toronto. So yes, I'm very happy to be here. Rohan has spoke to me off and on Twitter here and there when I post some things about analytics, usually trying to defend the Pittsburgh Steelers in one way or the other. I'm originally from Pittsburgh, PA. I had no choice but to be a Pittsburgh Steelers fan. My dad worked in the steel mills his entire life. I probably would have been disowned if I did not grow up a Steelers fan. Penguins fan, obviously. And unfortunately, I'm also a Pirates fan. It's been a rough stretch of 20+ years with the Pirates, except for that 2-year stretch in 2014 where we made the playoffs, got through Cincinnati in the wild card game, and then got swept in the divisional round. And now it's been just hello darkness, my old friend, all over again ever since. So as Rohan said, I have written a book called Introduction to NFL Analytics with R. The book covers everything from beginning to learning to code, learning the tidyverse, learning about dplyr, all the way to advanced analytics. And today we're going to jump into some of that advanced analytics stuff. We'll start off talking a little bit about linear regressions, which are not advanced analytics, but they kind of start the groundwork about why NFL data is difficult to work with before we get into the advanced analytics stuff. So a little bit about me. Why is my screen not changing? There it goes. I have my communications degree. My undergraduate degree is from a tiny school in the mountains of West Virginia called West Liberty. My master's is from Millersville, and then I actually got my PhD just down the road from Toronto at Western Ontario. I did a PhD in sociocultural studies. When I was doing my master's, I discovered that I was very much interested about the interplay between sport and society. Specifically the Olympics, about when the Olympics come to a city, the damage they do to that city, the infrastructure, the white elephants, all of that stuff. And it just so happens one of the preeminent scholars of Olympic studies, Bob Barney, is a professor at Western. So I ended up there. And then, as explained right now, assistant professor at Kutztown University of Pennsylvania, one of the 14 state schools in the Pennsylvania state system. Aside from teaching, I'm the provost assessment fellow and chair of academic assessment. So a lot of administrative tasks on my desk too, about assessment work and meeting learning objectives and all that fun stuff. And then as explained, I have recently written Introduction to NFL Analytics with R. It's out with CRC Press in their data science series. CRC Press is unique in that they believe in the open source doctrine that guides R in the programming language. So there is an open source version of the book online. If you just Google the title, the website will pop up. Exactly the same thing. It's just if you want a hard copy, you can jump onto Amazon and buy the hard copy as well. So the guide for this talk, we're going to, like I said, start off with regressions, start off with some simple linear regressions, work our way up to a few more advanced methods, and then work our way into digesting Tidymodels and building an XGBoost model within Tidymodels. I need to tell you upfront that I am a Tidymodels disciple. I believe in Tidymodels. I think it is a wonderful package. I know there are people out there who are probably bleeding from the ears right now hearing me say that because I believe in Tidymodels so much. But my belief is that if you're going to work in the Tidyverse, you might as well work with your models in Tidy format as well. And Tidymodels lets you do that. Plus, I think in the general scheme of things, if you're walking into learning advanced analytics for the first time with R, Tidymodels is a good framework to do so. You can do XGBoost within the XGBoost package or within base R, but Tidymodels is a good hand-holding mechanism if you're learning the process as well. I also want to try to get through this with time to spare for Q&A. I can get overly excited when I talk about analytics in sport and sometimes lose track of time. So if that happens, just literally start yelling at me that you have questions and you want me to explain something further, whatever it is. I'm pretty low key. So to get started, this is a short tibble of 2022 season data. Every team, so 32 rows here, with the total points that team scored and the total yards that team earned. So if we're going to look at a simple linear regression here, we can just say, okay, let's examine how many total points a team is likely to score against the total yards that team earned. So we can throw that into ggplot and do a quick line of best fit with the data. So a couple things at play here, in that you can see the Dallas Cowboys up here, the freaking Dallas Cowboys. They scored more total points than what we would expect for a team that has a hair of 6,000 yards. This bunching down here, the Seahawks, the Raiders, Jacksonville Jaguars, Minnesota Vikings, all have about the same amount of yardage, but they are much lower in total points than the Cowboys. And then the opposite is true for teams like the Indianapolis Colts, New York Jets, Denver Broncos. They scored less total points than what would be expected for a team with 5,500 yards. And yes, I purposely ignored mentioning the Pittsburgh Steelers being in that grouping as well. But it's one thing to say, hey, look at this pretty plot that has the lineup best fit. You know, we can garner some information on it. We can see that the Cowboys overperformed scoring-wise based on their total yardage, and that teams like the Colts underperformed scoring-wise based on their total yardage. But if we go back and actually throw this information from this short tibble of total yards and total points just into a basic linear model where it's total points versus total yards and spit out the summary, we get a bit more insight to what's going on here. And it's important to look at this because it kind of directs some other issues we run into with NFL analytics. So the first thing that jumps out is that the residuals here are terrible, right? They're huge. They're nowhere near evenly distributed around 0. So the minimum distribution here of -71 means that one team scored 71 more points than it actually did, or that the regression model says they should have. The max distribution of 68, one specific team scored 68 points less than their actual points scored. Why is that? Why do we have such a large residual here that are not evenly distributed? That's because working with NFL data is absolute chaos. NFL data is chaotic, it is messy, and that is part of the reason that the NFL has somewhat lagged behind other leagues in terms of fully adopting and understanding and using analytics. It's not like baseball, where with baseball analytics, you have the batter versus the pitcher. And when the pitcher throws the ball, they're calculating the spin rate and all that stuff. They can track the batter's swing. They can get launch angle, exit velocity, because it's not chaotic. It's a structured, easy to understand analytics playing field. With the NFL, you have 11 guys on offense, 11 guys on defense, all doing their individual thing at the same time. That may or may not actually have an impact on the play. If you follow along with the Big Data Bowl, they just announced the finalists for this year's Big Data Bowl, and one of my favorite entries was research. So if you're not aware, the Big Data Bowl is when the NFL releases their proprietary tracking data. Every player has a tracking chip in their shoulder pads, tracking chip in their helmet, and their speed, their direction, what way they're looking is tracked every 10th of a second, stored in databases. That's all kept under lock and key by the NFL, except for the Big Data Bowl when Mike Lopez releases about 7 weeks of it, gives a prompt for research, and people try to find meaning in that mess. And there was an entry this year that did a research on say a running back takes a handoff and starts to do an outside run, but the defensive end gets one hand on him, but doesn't make the tackle. It's not necessarily a missed tackle, but NFL statistics aren't going to record that little hand on the running back. Their study showcased that that defensive end getting a hand on the running back slowed him down by 0.005 miles per hour, changed his angle by so many degrees. And because of that slight change, that slight adjustment the running back had to make, the rushing in free safety was able to get to him tenths of a second faster, which saved 2 yards on that rush. So if that defensive end didn't get his hand on him, he would have gained 2 more yards. That is the chaos of NFL analytics right now, where there is so much going on the field at one time. It's difficult to really grasp it like we do with sabermetrics in baseball. So going back to this regression, what's going on here? What could have caused some of these issues? Off the top of my head, maybe a team just sucks in the red zone, right? So maybe a team is able to move the ball down the field with ease. And then when they get within the 20-yard line, they just can't score, right? That's going to impact this regression. If a team has a high number of turnovers, similar to what we just explained, they can drive down the field, but they're prone to turnovers once they get close to the end zone. And then the big one is we have to consider strength of opponent, right? If a team so think about in this season, the 2022 season, the Philadelphia Eagles and the New York Jets, their defense allowed just 4.8 yards per play that season. The other teams in their divisions have to play those teams twice. They have to play the top two defenses in the league twice. That context is not built into most NFL statistics. There's a movement right now with expected points added for quarterbacks trying to adjust their EPA for strength of opponent. It needs to be done. But generally, we don't have that context in NFL analytics, where if a team, if you have a quarterback going against the Pittsburgh Steelers, because I'm a fanboy, you lose the context of the quarterback always having one eye on TJ Watt to see what he's up to, if he's going to get by the blocking and make the sack. We don't have that context. So as we go forward with this, we have to keep that in mind, that NFL analytics, I'll say it again, is chaotic, it's messy, it is often the wild, wild west when it comes to trying to find context to throw into it. So we can move on from simple linear regressions to trying to make a prediction with a regression. So we can create one that predicts the type of offensive play call that the team makes based on what contextual factors we do have. So we can say, okay, we want to make a prediction, pre-snap, what kind of play is that team going to run? And we can do it using play-by-play data from the NFL first on whether it's going to be a run inside, a run outside, or a short or medium or long pass. With short passes, air yards under 5, medium pass, air yards between 6 and 10, and then a long pass with air yards 11 plus. Air yards being the distance the ball travels from the quarterback to the receiver, no yards after catch included. It's just basically a pure quarterback statistic. So to get that kind of information, like I said, we use play-by-play data from the NFL first, specifically NFL Radar, pulling in play-by-play data from 2006 to 2022. It's important to note that the 2006 date was not randomly chosen. It just so happens that 2006 was the first year that air yards was included in play-by-play data. So if you want to do anything that requires air yards, you have to start with 2006. Doing some prep here, so selecting the variables within the data that are probably going to have some kind of impact on what kind of play is run. So the game ID, game date, that's for merging purposes later on, but game seconds remaining, the yards gained, yards to go, what down it was, where they were in the field, who the offensive team was, who the defensive team was, the score, whether a binary 1-0, whether the offensive formation was shotgun, was it a no huddle, how many timeouts are remaining, doing some feature engineering down here. So was it in the red zone? Were they in field goal range? In my argument, anything within 35 yards is pretty much field goal range for any competent NFL kicker. And was it a 2-minute drill? So, and then dropping a few things that weren't going to work very well within the data afterwards. And then prepping the data. And I made a very dumb discovery during this process. We'll get to that in just a second. So grouping by the game ID and the offensive team, and then just running a mutate where a run inside are those cases when play type equals run and run location equals middle, and doing that for all of our different predictions on what we think the play might be. A few more feature engineering where we're calculating the total runs, total passes, what the previous play was. The issue with this, though, is when I ran this code, I was expecting it to take seconds, like usual. I sat there for 22 minutes waiting for this to run. And I was like, I can't keep on doing that. Like, if this model messes up, I got to go back and rerun this. What is the issue? And I found out after some Googling and some messaging on Slack with the R for data science people, we discovered that there was an issue. There was a bug when you run a mutate and a case win within a group by. For some reason, it like bottlenecked the entire process. So instead of running case win right here, I switched over to fcase from the data table package, and it ran in 19 seconds. dplyr made the update afterwards to version 1.2, and it ran in 17 seconds. So if you ever run code that takes 22 minutes, it's probably not you. You probably discovered a bug in one of the packages. So keep that in mind. So now we go into Tidymodels. We have our data. We have our variable, the play type that we're trying to predict with all the other feature engineering items that we threw into it. So using Tidymodels to split the data, using R sample, so doing an initial split on our model and doing stratification by play calls, so we have an even number of all the different play call types between the testing and training, splitting it into training and testing, and then creating our folds so we can do cross-validation during the modeling process. Building the recipe with Tidymodels. So the recipe is basically, I would use the word more feature engineering within the modeling process. So basically we're saying the recipe, it's the regression, play call against everything else. And then all this stuff here are what are called recipe steps. So we're updating a couple roles to variable IDs, meaning, the season, the post team can stay in the data, but don't include that in the model. That's just for identification purposes later on. On step ZV is 0 variates, so any variable that has 0 variates will be automatically removed. Step normalize, it applies both the mean and the standard deviation from the training set to the test set. That's important because if you don't normalize the data between the split, you're going to have data leakage. And that's especially important when you're working on information that is based by season in the NFL, or if you're doing something by game, you want to make sure that that split doesn't leak. And then you want to have overfitting, or you want to have a model that has a 99.9% prediction rate because of that data leakage. And then step dummy is just taking, basically it's one hot encoding. So taking all this information and making it binary across the variables. So we take that information, we can build our model. In this case, we are going to tune for penalty and tune for mixture, where we're going to let Tidymodels decide what the best parameters are there. throw it all into our Tidymodels workflow, create our grid here. So in our grid, we're saying we want the Tidymodels to take this information and loop it over and over and over and over and over again on this grid. So for the penalty, we're creating a sequence of 20 numbers spaced out evenly on the log scale so that the trading process is conducted on each number in that sequence. And the same thing for the mixture, except we're giving it a more straightforward argument. So just creating a simple sequence of numbers from 0.05 up to 1, and then running the model on those mixtures over and over and over again to figure out what the best combination is. And then we can run the model. So in this case, what is nice about Tidymodels, it does include the possibility of doing stuff in parallel. I don't have a super powerful computer by any stretch of the imagination. I have 12 cores in my CPU, but it definitely speeds the process up to use all those cores. So registering the do parallel so I can use all the cores in my CPU. And then the tune grid, you just throw in your workflow, you throw in the folds that recreate it, you throw in the grid that recreate it. And the control, we're just telling it to save predictions. So all the predictions that it makes, we want those to save into a data frame so that we can work on them at a later point. At this point, when you hit run, you can just get up and walk away for a while. Yeah, I think this took like 4.5 hours to run. It is what it is. Without parallel processing, I don't want to guess how long it would take. So the results. So we can use the show best function to say, we want to see the best results that happened. So remember, we did folds, we did cross-validation, all those different runs on the model, what were the best ones? So we're looking at the top 5 best models. Not much difference. The mixture is the same at 0.2. The mean is the same. The standard error is the same. The only difference between these models really came down to the penalty, where a smaller number equates to a model with less regularization, and it allows it to fit more closely to the training data. So rather than say, okay, I just want to select model 1, or I just want to select model 2 and use that to run on the withheld testing data, we can use a function that's called select by one standard error. So it allows us to choose the model whose standard error is no more than one above the best model. So it kind of gives you the best of both worlds. We can take that, so you can see we did our final penalty here. Hold on, I lost my screen. We can just edit that out on the recording, right? Okay. So we have our select by one standard error here. We're throwing that into, like, that's our final penalty. This is our final combined model from all the folds and cross-validation. We're creating a new finalized workflow with that. So beforehand, the workflow was saying, find the best model on all these folds and all this cross-validation. Now we're saying we have our favorite model, rerun this with that specific model, and fit it against our withheld testing data. So we can throw that all together, which allows us to explore what the predictions were against what the play really was in the original data. So in order to determine how the model actually performed, the best way to do it, I think, given the structure of this model, was a ROC curve, which is a receiver operating characteristic curve. So what this shows, it's plotting the model's true positive rate against the false positive rate for each of the different plays in the data frame. So we can see the arching of this dark green line here for run outside. It's approaching the 80% line. So it was able to predict roughly 80% of the time when the play was going to be a run outside. So it did a pretty good job with that specific play. And then all the other ones, the model had slightly more difficulty in distinguishing and predicting, a long pass, medium pass, run inside, short pass. But that said, all those predictions are still pretty far removed from the line of no discrimination. So the line of no discrimination is this horizontal dash line, which is really no better than a coin flip. So the model, I would have bet my life on this model. If you told me to run this model with the Super Bowl in real time and predict what the team was running, and if I lost, I had to pay you money, I'm not taking that bet because, again, the NFL is chaotic and messy, right? This model can only take so much information. There's a lot of context missing within it. But what we can do is say, with the data we had at hand, at face value, an NFL offense is designed to be unpredictable. A good NFL offense should be able to catch the defense off guard. So with that in mind, the fact that we were able to estimate pretty well when it was going to be a run outside, it's not too bad. So we can take this data and just say, okay, who were the most predictable offenses from this model? If you are a New Orleans Saints fan, I am sorry, because they are the most predictable offense 3 times in this data. So the most predictable offense, the 2017 New Orleans Saints, they ran 925 plays that season, and our regression model was able to correctly predict 58.7% of those plays. All the way down to the Washington Commanders in 2015, who had 53.2% of their plays predicted. And then the model with us, off the top of my head, I think the worst performing one was like 8% or something. I had a really hard time with some teams. But again, I don't put much weight into that because, repeat with me, the NFL is messy and chaotic. So we can move away from regressions into more advanced stuff and start building an XGBoost model. So we can build one that looks at rushing yards over expected. Rushing yards over expected is a model that, based on the input, predicts how many rushing yards a running back should have gotten on a play. And then through subtraction, how many rushing yards over expected did that player have, or how many rushing yards over expected did that player not have? Basically a performance indicator. So again, just prepping the data here, again with play-by-play data. So getting the game rush count, so the cumulative sum of rush attempts for every running back in every game. The rush probability, there is an expected pass variable within the play-by-play. So building, okay, we can find the converse of that based on some simple math. Strategic score, just some more feature engineering, meaning taking the rush probability divided by how many defenders were in the box on that play, taking a look at the winning percentage, sticking with the red zone, field goal range, 2-minute drill, and then taking it into Tidymodels again. And this time we're doing a bit more work as opposed to what we did with regression. XGBoost is a much more powerful process. So here we are tuning for lots of stuff. We want the model to determine the right amount of trees, the right amount of tree depth, the best amount of loss reduction, the learning rate, etc. It's also important to point out that in the engine, instead of XGBoost, I am using what's called light GBM. It's the exact same thing as XGBoost, but it works in a different fashion. So, and it's typically faster than XGBoost. And that speed increase is because light GBM as a package builds the trees in a vertical growth pattern. And XGBoost, when it does its tree building, does it in a horizontal fashion. The vertical growth pattern that light GBM uses is faster. There's no doubt about it. It can run a model faster, but it's very, very prone to overfitting when you do it in the vertical growth pattern, which is why we went from tuning 2 hyperparameters to tuning all of these hyperparameters, because we want to avoid that overfitting that light GBM often provides. So we build our model with all those tuned hyperparameters. And just like before, we run the model, and this time we are selecting the best metric. We're just letting the model decide based on all those tuning parameters what the best model was. And in this one, it is telling us, hey, this model was the absolute best one that ran. So just like before, we take that best model, we fit it into a finalized workflow, fit it to the withheld testing data, and then run it against the predictions. So then we can take the actual yards that the running back got and then look at what the model predicted that running back should have received on that play. So we can take that information, throw it into a GG plot, and just take a look at actual rushing yards versus expected rushing yards. So this is from 2016 through 2022 again. So looking at this, Nick Chubb, the Cleveland Browns, boo, as a Pittsburgh Steelers fan, Nick Chubb, 5,982 total rushing yards. The model expected him to get 5,097. So he had 885 rushing yards over expected during this time period. Joe Mixon, on the other hand, gained 5,025 rushing yards. The model expected him to get 5,156. So he was 131 yards under expected based on what the model was going to give him. So rushing yards over expected, we talked about the big data bowl a little bit ago. It was actually something that was created out of the big data bowl. And I did a presentation a few months ago at a research conference about trying to build expected rushing yards over expected model without that tracking data. And this model is actually not too far off what people were able to build with tracking data. The biggest one was Derrick Henry. He was several hundred yards off for a couple seasons, and I still haven't figured out why, but everybody else was within 100 yards or so without that tracking data. So in terms of creating a model, this one's pretty accurate even without the tracking data and using XGBoost. So like I said, I can go on and on and on about this stuff, but I want to open the floor to any questions you have about NFL analytics. I'm not against live coding. If you want to see something done, if you have a question that you want answered, especially about why the Steelers are awesome, I'm happy to live code that for you. If you want to know who's going to win the Super Bowl, we can take a look at Brock Purdy stats against Patrick Mahomes stats. And Rohan and I were talking earlier, like it has to be Patrick Mahomes. You gotta take the experience over freaking Brock Purdy. All right. So any questions you have, like I said, I'm happy to live code. I can pull up our studio and show you how to do stuff. The floor is yours. I want you to get out of this what you want to get out of it instead of listening to me ramble about things.
That's amazing. Thank you so much, Brad. Incredible presentation.
Thank
I'll
you.
stop recording.